Our next speaker is Mancinska from the University of Copenhagen.
Thanks. It's my pleasure to be back in Natal. So for those who were here last week, I have to apologize. The first few slides is going to be a repetition. But I'm going to try to wake you up so when you need to start paying attention if you want to. Okay, so I'm going to talk about conic relaxations of quantum isomorphism. It's going to be isomorphisms of graphs. So these are two graphs, and they are isomorphic. So idea of isomorphic graphs is that you actually have the same graph, but maybe you've labeled the vertices differently, so you don't see that. Okay. And then you're given these two graphs, and you would like to know whether or not they are isomorphic. But then if you want to be more formal, then you say that you have a mapping, F, which takes vertices of one graph to those of the other, and you ask that this F is a bijection, and that it preserves both adjacency and non-adjacency. So if you take adjacent vertices, you map them, you get two adjacent vertices, and the same if you took two non-adjacent vertices. You map them, you get two non-adjacent vertices. Okay, and so whenever such a mapping F exists, we say that the graphs are isomorphic, and I'm going to denote it using this congruent symbol. Okay, but now I want to think about isomorphism through this kind of interactive protocol or non-local game, where I have two provers, Alice and Bob, and they are working together, and they play this game against a verifier. And the idea behind the game is that Alice and Bob try to convince this verifier that the graphs are indeed isomorphic. So the game goes as follows. The verifier picks two vertices, x and x prime, and these could be vertices of G or vertices of H, and it could be that x is from a vertex of G and x prime is a vertex of H, or the other way around, right? So all the possibilities. And I want to think of the vertex sets of the two graphs formally disjoint, so that whenever Alice or Bob gets a vertex, they know which graph this vertex comes from. All right. So now after Alice and Bob receive x and x prime, they are required to respond with vertices from the other graph, right? So if you are a player, Alice or Bob, and you get a vertex from G, then you should respond with a vertex from H. The other way around. If you get a vertex from H, you should respond with a vertex from G. And all right, and we don't allow Alice and Bob to talk to each other. Maybe the battery died. Okay. All right. So we are not allowing Alice and Bob to talk to each other after they receive this x and x prime, because otherwise the game sort of would become trivial. However, like both Alice and Bob know these graphs G and H before the start of the game, so they could agree on the strategy that they are going to use to play this game before they receive this x and x prime. All right, and now after the verifier receives the answers y and y prime back from Alice and Bob, he's going to announce whether Alice and Bob win the game or they lose the game. And now remember, we required players to respond with vertices from the other graph. So when verifier has received y and y prime, if he looks among x and y, there's precisely one vertex from G and precisely one vertex from H. And the same for x prime and y prime. We don't know, right, if x prime is from G or y prime is from G, but one of those vertices is from G, the other one is from H. Right? And then he's going to say that the players win if there is a typo here. Okay, so if the G vertices of the players are related the same way as their H vertices. So don't read the output vertices. It should say G vertices are related the same way as the H vertices. And this related, it can mean one out of three different things. So I'm going to distinguish when vertices are the same, they are distinct, non-adjacent, or they are adjacent, right? So for instance, if x and x prime were two adjacent vertices of H, then y and y prime need to be two adjacent vertices from G, okay? And some more complicated combinations. All right. Right, and then we sort of want to know for which graphs G and H can Alice and Bob win this game, for which graphs does there exist a strategy which allows Alice and Bob to win this game irrespective of which X and X prime the verifier selected. And whenever I'm going to say win, I'm going to mean this: win irrespective of the vertices received. Okay. So let's just see how Alice and Bob could play. So for instance, if the two graphs are isomorphic, right, so then there exists this mapping F, which is a bijection, adjacency, non-adjacency preserving G to those of H. And then Alice and Bob can agree on this isomorphism F, and they would simply respond with F of the vertex they received if they received the vertex from G, or they would respond with F inverse of the vertex they received if they got a vertex from H. Okay? And then you can check that all these conditions that I input in the game, those all would be satisfied. All right. So what this says is that whenever the two graphs are isomorphic, there does exist a strategy that allows Alice and Bob to always win. There exists a winning strategy. Now, it's not too hard to see that actually the converse holds as well. So that when this is how we sort of define this game. We wanted this property that whenever there exists a perfect strategy for this game, then the graphs actually need to be isomorphic. Okay. All right. So, so the graphs are isomorphic if and only if classical players can win this GH isomorphism game. And therefore, we can define this quantum isomorphism simply as the existence of a perfect quantum strategy in this game. So the first one is something we prove, right? This correspondence with classical players. And the second one is something we define. All right, and what is a quantum strategy? Well, I need, so the game remains the same. All that changes is sort of the actions that are available to Alice and Bob. So a quantum strategy, it consists of a quantum state. So some shared state psi, it's going to be a unit vector in some CD tensor CD. And then you think of this one tensor as belonging to Alice and the other one to Bob. Right, and then when Alice gets her vertex X, she can decide what sort of quantum measurement can perform her part of the state, and she will try to use the outcome of the measurement to help her come up with an answer. And we assume that the measurement outcomes are labeled by the vertices of the two graphs. So essentially what you have is Alice has a measurement, script EX, for every question she might receive, and then this measurement consists of PSD matrices EXY, and these Y's are vertices of the two graphs. And because it's a quantum measurement, these EXYs need to be PSD, and they need to sum to identity if I fix X and sum over Y. Similarly, Bob has some sort of measurement, so sets of these PSD matrices. Right? If Alice and Bob follow this strategy, so they share this state psi, and then they perform these measurements, then we can compute what's the probability that upon receiving vertices X and X prime, they respond with Y and Y prime, and it's simply going to be given by this inner product formula. So you take the shared, this vector psi, you take the inner product with psi when you have applied this EXY tensor Fx prime Y prime. And so for quantum isomorphism, we are interested in when does there exist a quantum strategy that lets the players always win. So when can we choose this state psi and these measurements so that this joint conditional probability distribution lets Alice and Bob win in this game. So what does that mean, that this joint conditional probability distribution lets them win? Well, we want that sort of the probabilities which correspond to Alice and Bob losing in the game, right? The cases where the verifier is going to say, Alice and Bob, you lose, that the probability that they output such things is 0, right? So we want a quantum strategy, these PSD matrices and vector psi, where certain entries in this P are 0. Okay? All right. And this is sort of now a starting point for this conic relaxation. All right. So now we just think of this joint conditional probability distribution as a bunch of numbers, right? And we're going to arrange these numbers in a matrix. And we remember that we wanted certain entries to be 0 because they corresponded to Alice and Bob losing in this game. Right, and now we define this K isomorphism matrix. K, I could select my favorite matrix cone if I wanted to, but I will look at some specific cones. All right, so I say that some matrix is a K isomorphism matrix if the following things hold. So first of all, the matrix should be in the cone K. All right, and then the rows and the columns are going to be indexed by pairs of vertices, one from G, one from H. So both rows and columns are indexed by these pairs. And then I put these conditions on my matrix elements. So I require that certain block sums sum to 1. And essentially what it is capturing is that like if I fix this x and x prime, so this is the question, and I sum over y and y prime, then these things should form a probability distribution, because this PYY prime given XX prime is the probability that Alice and Bob respond with Y and Y prime when they are asked X and X prime. Okay, and then I require that certain entries are 0, so that, namely the entries which correspond to Alice and Bob losing in this game. All right, and then whenever such a K isomorphism matrix exists, we can say that the graphs G and H are K isomorphic, where K is some matrix cone. And the cones I'm going to look at are the following ones. All right, so the first one is that of PSD matrices, right? So positive semi-definite matrices, I'm going to call it S+. Then the next one is the doubly non-negative cone. So a matrix is doubly non-negative if it is PSD, and it's also entry-wise non-negative. So that's easy. Now, next one is the completely positive cone. So another way to think of PSD matrices, right, is those are gram matrices of some set of vectors. So like the ij entry is given by the inner product between vi and vj. Now, matrix is completely positive if I can moreover pick these vectors to be non-negative, to have non-negative entries themselves. Okay. All right, so now the next cone I'm going to look at is this completely PSD cone that we already heard in Mario's talk. So this was recently introduced by Monique, Laura, and Teresa Piovesan. And this is sort of, you can think of them as like gram matrices of PSD matrices, right? So every entry in this matrix M is given by the inner product between PSD matrices, right? And I've fixed these. Okay, so these are the cones we look at, and so it's known, of course, like if I wanted to be kind of rigorous, I need to fix the size of the matrices for this to even make sense. But if I fix the size of matrices n, and my n is big enough, then actually all these inclusions are strict. I think n needs to be at least 5, and then they are all strict. And just because I have this chain of inclusions for these cones, remember I defined these K isomorphisms as like existence of a K isomorphism matrix. So if I have, say, a CP matrix, well, it's also an S plus matrix, or it's also a CS plus matrix. It's not too hard to see that these implications hold. So just from these cone inclusions, I get this chain of implications for my conic isomorphisms. Okay. And now it turns out that we can characterize these quantum and classical graph isomorphism as a conic problem if I just pick my cone correctly. So for classical, so just regular graph isomorphism, the corresponding cone is this completely positive one. And for quantum one, it is the completely PSD cone. Right? So my graphs are quantum isomorphic if and only if there exists a completely PSD matrix, which is a K isomorphism, which is an isomorphism matrix for these two graphs G and H, right? So it has these box sums and it has zeros in the right spots. Okay, and so we know that quantum isomorphism is actually a very hard problem. So it is undecidable. It's the hardest type of problem we could think of. And so the way we show it is by making use of William Sloster's breakthrough result, where he showed that computing the quantum value is an undecidable problem for a specific class of games, namely linear system games. So then what we do is we take a linear system and we build a pair of graphs. And we do this translation in such a way that the linear system is quantum satisfiable if and only if the graphs are quantum isomorphic. So we have reduced the quantum satisfiability problem, which was shown to be undecidable by William Sloster, to testing quantum isomorphism, right? So that implies that quantum isomorphism is undecidable as well. All right, so sort of bad news, right, for quantum isomorphism. So like if you give me two graphs, I don't know how to tell you if they are quantum isomorphic or not. And therefore it would be like, and this is how we started actually looking at these conic relaxations, because we thought we could relax, right, our cone. So we are interested maybe in this cone, but we could relax it to DNN or S plus to possibly rule out the existence of quantum isomorphism for certain pairs of graphs. Okay, so now let's take a look at this DNN and S isomorphism. And we're gonna see some, so the basic idea for these cones is the following one. So we take our graph G and then we associate some special kind of algebra to it. And we would like to choose this algebra so that the two graphs are isomorphic with respect to this cone, if and only if the corresponding algebras are isomorphic. And what kind of isomorphism I'm requiring for algebras, that's going to depend on which specific algebra I have. So I will want that sort of the isomorphism behaves nicely with respect to all my algebra operations. All right, and kind of, so this part with these conic relaxations, it's not, well, they are relaxations of quantum isomorphism. In that respect, they are quantum problems. But like the, if you just formulated it as looking for this K isomorphism matrix, the problem has nothing quantum intrinsically in it. But then we were kind of inspired by this tool that we all use in quantum information, so where we think of linear maps characterized by their Choi matrices, right? So then what we do is we take this K isomorphism matrix and we think of it as a Choi matrix of some linear map. And then it happens that this linear map is gonna provide us with this isomorphism between these algebras. So that's kind of the overall idea. But now specifically for DNN-isomorphism, it turns out that this characterization is provided by algebras of graphs. And these are algebras that are well known in the literature. Okay, so we were able to show that two graphs, G and H, are DNN-isomorphic. So there exists this DNN-isomorphism matrix, if and only if the coherent algebras of the two graphs, G and H, are isomorphic via some isomorphism which maps the adjacency matrix of one graph to that of the other. Okay, so now I'm going to tell you what the coherent algebras are. Okay, so first, the coherent algebra of a graph is the smallest coherent algebra which contains the adjacency matrix of graph G. Okay, now you ask me, okay, but what's coherent algebra? All right, So an algebra is coherent. Well, okay, first of all, it's a matrix algebra. So you can multiply matrices, take linear combinations, and all that. But for it to be coherent, you need to satisfy the following conditions. So first, you need that the identity matrix and the all ones matrix, I'm calling it J, is in your algebra. And then you need that your algebra is closed under taking complex conjugate transpose. And you also need that your algebra is closed under taking the Schur product, the entry-wise product. It's like how you multiply matrices if you didn't know how to multiply matrices. Okay, so this is a coherent algebra, right? And so the two graphs are DNN-isomorphic if and only if the corresponding algebras are isomorphic. And so this is a studied relation on pairs of graphs. When do two graphs have isomorphic coherent algebras? And therefore, we kind of get some connections to like descriptive complexity and logic. So we get that the DNN-isomorphism of two graphs is equivalent to the graphs not being distinguished by a two-dimensional Weisfeiler-Lehmann algorithm. So this is a family of algorithms. For every dimension, you get a Weisfeiler-Lehmann algorithm. And if you fix the dimension, then they run polynomial time. So you can also, I didn't talk about that, but you can think about non-signaling isomorphism. And then it turns out that it's equivalent to graphs GNH not being distinguished by one-dimensional Weisfeiler-Lehmann algorithm. And if you wanted to kind of capture all these Weisfeiler-Lehmann algorithms, then it turns out that like the k-dimensional Weisfeiler-Lehmann is equivalent to kind of a different game where you have more provers. So the number of your provers would be k-1, and you try to play an isomorphism game. So the existence of a perfect non-signaling strategy would then be equivalent to the graphs being corresponding Weisfeiler-Lehmann algorithm. Okay. But one further connection we get to logic is that, okay, no, all right. So there's also a logic formulation of these Weisfeiler-Lehmann algorithms. All right. Don't remember that. Okay. But one good thing is because this Weisfeiler-Lehmann algorithm runs in polynomial time, right? I think this one is going to run even in expected quadratic time. So we can test this relation, isomorphism, efficiently, right? So that's good news because it relaxed this quantum isomorphism, which was undecidable. Okay, and then we also know that if you take two graphs and they are strongly regular, so this sort of means like they are very well-structured graphs. So formally what it means that the degrees of all the vertices are the same. And now if you look at the number of common numbers of any two adjacent vertices, then that's some fixed number that doesn't depend on the vertices you picked. And the same holds true for non-adjacent vertices. So if I pick two non-adjacent vertices, I look at how many common neighbors do they have, then this number does not depend on the specific vertices I picked, as long as they're non-adjacent. Okay, and now for PSD isomorphism, so we have a similar algebraic characterization. So you can define some algebra. Now you're not allowed to take Schur products with arbitrary elements in your algebra, but you only need to be closed under taking Schur products with identity and the adjacency matrix. As far as we know, this does not coincide with some sort of previously studied relation on graphs. But we can show that if the two graphs are PSD isomorphic, then they need to be cospectral, they need cospectral complements, cospectral Laplacian matrices, various types of cospectrality, and also some structural similarities. And one nice thing that we get is that, so this, if the two graphs you look at, they are what's known as one-walk regular, some special type of graphs, then actually it suffices to check if the two graphs have the same spectrum to determine whether or not they are PSD isomorphic. Okay? So for these graphs, cospectrality is equivalent to PSD isomorphism. Okay. All right, now I want to just sort of enter the finishing phase and just show you some pictures. Okay, so this was the chain of inclusions, right? So this, we looked at this completely positive isomorphism. This was like the classical one. Then this was the quantum one, completely PSD. Then this is doubly non-negative. Nice cones to optimize over. So what I want to show you next is that sort of none of these relations are the same. So that there are always examples that are isomorphic, isomorphic with respect to the relation on the right, but not on the relation on the left for every one of these arrows. So these are truly different notions. So this is the smallest known example of non-isomorphic graphs, which are quantum isomorphic. You probably already saw this picture if you were at my talk last week. So we get it from this reduction from linear BCS. These graphs correspond to the magic square game. This is the smallest pair of graphs that we know that are not isomorphic, but that are quantum isomorphic. Okay, so here's an example of graphs which are DNN-isomorphic, but not quantum isomorphic. The reason why these are DNN-isomorphic is because clearly, yeah. So these games even these graphs have names. Like I didn't make up the names. So I guess the rook graph is the moves a rook can make on a chessboard. So they are DNN-isomorphic because they are one-walk regular and they are cospectral. And any such pair of graphs, we know that they are DNN-isomorphic. And they are not quantum isomorphic because we were able to show that if you look at the complements of these graphs, then they don't have the same quantum chromatic number. Okay, so this is 4 cube, right? So just like strings of length 4, and then you connect the ones of distance 1. And Hoffman graph. So these are two strongly regular graphs with the same parameters. But these graphs don't have the same diameter. So that's how we know that they are not DNN-isomorphic. All right, so now let me just summarize. So what we just saw, right, that these all these relations are really different relations on graphs. So our starting point was to think of graph isomorphism in terms of this interactive protocol where Alice and Bob talk to a verifier and they're trying to convince the verifier that the graphs are isomorphic. Right, and then we showed that if you have a classical strategy that can always win, then this can happen if and only if the graphs indeed are isomorphic. And then we thought, okay, what happens if you now give Alice and Bob more power? What happens if you allow them to share entanglement and do quantum magic, right? And then we saw that sometimes, even though the graphs are not isomorphic, Alice and Bob can still convince the verifier. Okay. And then we also looked at these conic relaxations, right, of quantum isomorphism, because it turned out that quantum isomorphism is not decidable. So in general, given two graphs, I don't know how to tell you if they are or are not quantum isomorphic. So we looked at the doubly non-negative cone and PSD cone. And then, all right, so I showed you these examples where you get, you see that all these are new relations. And we saw that DNN-isomorphism we can test in polynomial time using this Weisfeiler-Lehmann algorithm. This is actually equivalent to a previously studied notion on relation on graphs. And it's like unfortunate coincidence. So this relation on graphs, it's called graph equivalence. It would be cumbersome to say it is equivalent to the equivalent relation on graphs. All right, so about complexity. So we know, right, because of Baba's recent breakthrough result, that we can test isomorphism in quasi-polynomial time. Okay, so we can test this DNN one in polynomial time, expected quadratic time because of this Weisfeiler-Lehmann algorithm. Then we know that this quantum one is undecidable. We don't know the exact complexity of PSD isomorphism. All right, that's all I wanted to tell you so far. Thank you very much.
Thanks, Laura, for the very nice talk. Any questions?